Okay. Hello, everyone. Welcome to the first video on the lecture material. By the time that you see this video, you will also see the slides uploaded. And regarding the slides, I did my best to put as much detail as I could on the slides so that they are hopefully self-explanatory, which is of course because, well, due to the COVID situation, we cannot interact in the classroom. You cannot directly ask me questions. So I tried to give you as many details as I could on the slides. In case there is something unclear, please write me a message and then we can discuss any questions during the tutorials. Okay, so I would say we jump directly into the material. By the way, so you're not the only one struggling with the COVID situation. This is the second attempt for this video. I just spent half an hour talking to the wall because it did not record any sound. Okay, so here the second round. Yeah, this course is about both cross-sectional and panel data, but mostly we will view the models from the point of the panel data. Now, what is panel data, you may ask? Well, panel or longitudinal data consists of n individuals, which can be really individuals in the sense of people. It can be households, can be firms, it can be countries, it can be whatever you want. The condition that we have is that each of those individuals is recorded over at least 2 periods of time in order to have a panel. So panel data combines a cross-sectional dimension, and the length of the cross-sectional dimension is denoted by n, with a time series dimension, and the length of the time series dimension or the panel length is denoted by t. Now, in microeconomics, we typically have many individuals in a sample, but we have only very few time periods per individual available, which is because, well, collecting panel data is very costly, right? You have to sit on the phone and every year call a company, call individuals, ask them a questionnaire. People will drop out. It's very costly to track people, and therefore you only have typically very few data points in the time series dimension, yeah, where you have many data points in the individual dimension. And this is why mostly when we do asymptotic theory, we will keep t fixed and let only n go to infinity. And only when we talk about nonlinear panel data models, we will actually let both n and t go to infinity. You see that this is slightly different from what you may know from time series data. So where you have maybe multivariate time series where t goes to infinity and n may be fixed or may go to infinity slowly. So in our case, we let n go to infinity and either keep t fixed or let t go to infinity slowly. Okay, now panel data was kind of like something esoteric not too long ago. But nowadays, panel data is something that is widely applied. It's hugely popular. So when you do panel data, both in theory and in applications, this stuff gets published in very good economic journals. And panel data nowadays even has conferences dedicated to only panel data analysis. And one reason for the increase in the popularity is that nowadays we actually have some nice panel data sets available. So for instance, one of the most famous and actually the oldest one is, at least to my knowledge, is the panel study of income dynamics in the US. We also have a national longitudinal service also in the US. Then there is some stuff in Germany. Then there is some stuff in CompuStat. So nowadays we actually do have nice panel data sets, and therefore it's also interesting to develop theory to exploit the power of this data. Talking about the power, we already mentioned that panel data sets are very costly to collect. Yeah? So you have to track people, and that's just not only annoying, but it's also costly, right? So why do we need this data? What is the big advantage of this data type? Well, the first obvious thing is that, of course, if you have 100 individuals over 5 time periods, that gives you 500 data points, right? So that can be like simply regarded as having more data than simply a single cross-section of 100 firms. However, that's not really the main benefit that we are interested in. So the first main benefit is that we have a set of individuals that we record over many time periods, and this gives us an opportunity to actually observe dynamics over time. Yeah? So with that, we can actually identify and estimate effects that we would not be able to estimate without additional assumption, simply using a cross-section, right? So if you only have a cross-section, that means you have a snapshot of, well, of a situation in a particular point in time, and panel data gives you really a development over time. Why is that important? Well, first example, let's we ask ourselves whether being in a union actually has a positive effect on your wage, like a causal effect. However, you only have a cross section. Now, you do a regression and you regress like wage on the dummy of union membership and some other control variables, for instance, age, level of education, sector, right? And you find a positive significant effect of union membership. Now, does this really mean that if you join a union, that increases your wage? Well, it may also be that simply in the group of the union members, you self-select the more productive individuals, right? So therefore, it can be that if you, as a completely useless individual, right, you join a union, that will not increase your salary, right? Because it's kind of really this productivity that is playing in the background that yields the higher salary for the union members. Okay. Next example. So we have a classic paper and we look at the labor force participation of married women. And what is observed in this paper is that there is a participation rate of 50%. Now, if you have a cross-section, meaning a snapshot in a particular point in time, that can be explained in many ways. Two of which are the following. Well, each woman works 1 year, then 1 year unemployed. 1 year, 1 year unemployed. Then in the whole population, you would have 50% of the women working at the time, right? That could be one explanation. The other explanation could be that you have half of the women working all the time, whereas the other half never works, which also gives you a participation rate of 50%. And you can have all sorts of mixtures between these two extremes. Yeah, so without actually observing the dynamics over time, both explanations are equally valid, and you really cannot say, well, what's the point here, right? Okay, a next big thing is from the treatment effects literature. Yeah, so we have a dedicated lecture on the estimation of treatment effects. That should be the fourth lecture. Now, suppose you have a treatment in the form of a policy intervention. Here we say we have an increase in the minimum wage. The fundamental issue for the estimation of treatment effects, as it says here, is that once you are treated, it is impossible to know what would have happened to you if you had not received the treatment. Right? So think of the treatment, for instance, as a pill. I give you the pill, you take it, and afterwards, your development in terms of health, I don't know. I cannot tell what would have happened if you had not taken the medicine. Now, the problem, therefore, is that you don't have a good control group. You don't have a good comparison group for each treatment. So one way to find a comparison group is you simply go to a neighboring state and you take a set of workers there and you compare them with the set of workers in the state where the treatment took place. However, there may be issues with that because the treatment group state may be substantially different or structurally different from the control group state. You cannot simply compare people in California to people in Alabama, right? Because there's macroeconomic differences that will make the effectiveness of this treatment that will make the people in Alabama a bad control group for the people in California. And therefore, you cannot get causal relationships without any further assumptions. And what we will see is that when we have panel data, or at least repeated cross-sections, we can actually do something. Yeah? So we can relax some of the assumptions to get causal estimates. Now, finally, we look at the single time series. Now, So think about, you want to simply assess whether innovation actually has a positive effect on the sales of firms. Yeah? So firms spend a lot of money on innovation. Does that actually help them in terms of sales? Now, if you only look at one single firm and you look at this firm over time, well, that's nice to know about this firm, but you cannot generalize from that single firm to the population of all firms, of course, right? Because firms from different sectors may be very different. Yeah? Like you cannot compare a firm in the tech sector to a firm in the manufacturing sector. And well, the answer to your question, whether innovation helps firm sales, may also depend on whether you have picked a winner or a loser in the innovation race. And the example that I picked here, I'm not even sure if you guys still remember this kind of stuff, right? There was like a time where people actually used DVD. There was no Netflix and this kind of things. And there was a high definition DVD. Yeah? This one was actually called high definition DVD. And the other thing was the Blu-ray. Yeah, both were very similar innovations, very comparable, but the Blu-ray was the one that was accepted by the consumer, and this thing went down in flames. Here, big sales, here, like oblivion. Yeah? So the choice of your firm will, of course, be very important for your answer to the question. Okay, that is the first thing. So panel data allows us to observe a big number of individuals over time. Yeah? So with that, we can generalize to the population of all individuals in the population, right? At least as if there's a random sample. And we can look at dynamics over time. Now, besides observing the dynamics, the second really big advantage of panel data is what I call here some sort of statistical magic. Yeah? The magic is that with panel data, we can control for variables that are completely unobservable. Yeah? We are never able to see those, and sometimes they even have, we don't even know what kind of unit they have. The only condition that we need is that those variables are time invariant. Yeah, we can think of these variables as being your individual preferences, inherent ability, your productivity, or when we talk about firms, we can think about management quality and these kind of things. Huh? Now, these are variables that are interesting, but for instance, your preferences don't really have a natural unit of measurement. Yeah, so we may not be necessarily interested in the preferences per se, but we want to account for your individual preferences because your preferences may be correlated with observed characteristics. And therefore, if you do not account for preferences, you may end up with an omitted variable bias, yeah? Which is of course bad. Yeah? So, sorry. Having panel data allows us to account for these unobserved variables and therefore remedy omitted variable bias, which is something fantastic. Now, to give you an example of this, let's see, or let's try to assess the effect of education on wage. So that should be very interesting to you. Does going to university actually help you in receiving a higher salary? You could try to estimate this by simply running a regression with wage on the left-hand side, and on the right-hand side you have the level of education, and you have some additional controls like your age, your experience, the sector, and all this kind of stuff, right? Now you do this and you find that there is a very large positive and significant effect of education. Wonderful news, right? Maastricht University is very happy. If you go to Maastricht University, you make much more money later on. However, you may have to be careful here that you're not too enthusiastic because there may be a potential omitted variable bias. Yeah, so let's think of variables that we cannot control for. Yeah? So for instance, inherent ability, intelligence, or motivations of students. And now let's think of a story that we like to tell ourselves, that people that are very able, that are very intelligent, very motivated, they tend to get a higher level of education. Yeah. So these people, they go to university, and in the rest of their life, they also receive a higher salary. However, it is of course not necessarily only the education that you received, it's also your motivation and your intelligence that drive the higher salary. And if you do not account for these variables, then all the effect of these variables will be subsumed in the effect of education, and therefore you will overestimate the effect of education. And therefore it's so important to have panel data. If you have panel data, you can simply account for these unobserved time invariant variables and therefore get credible causal estimates for the effects of education. Okay, so that's about the benefits and the motivation of panel data. Let's also quickly talk about our concept of causality in microeconometrics, because I'm sure in time series data and time series analysis, you heard some concept of causality, which is related to the model error terms, whether they are from the past or whether they're from the future. Here we have some view of causality, which is closely related to a conditional expectation. Now, let's go step by step. Let's start with economic theory, where we want to explain a variable y with some other variables x1 to xk. Yeah? So we kind of have a theory about the causal relationship between these variables. For instance, your theory may say that the savings rate y increases when x1 increases. x1 is the income. Yeah. Or, well, let's go a little bit slow here. First, we say that y is a linear function of the characteristics x1 to xk. Okay. So that would mean that if the income increases, then the savings rate changes proportionally. Now, of course, the theory would also say that the partial derivative of g with respect to x1 is positive, meaning that if income increases, then you tend to also save more. Now, this relationship is completely deterministic. There is no randomness, there is no error in there. Really, it's a like completely deterministic system, which means that I give you the values x1 to xk. I can tell you exactly what is your savings rate. And I can also predict exactly what is going to be your savings rate if I increase your income marginally. Yeah? So this is like completely deterministic. So this is kind of what we think of at the ceteris paribus understanding of causality. X2 to xk are fixed. The only thing that changes is x1. And if you then observe a change in y, that means that this change has to be due to this. Yeah? So this thing is causing a change here. Now, this is in theory. Of course, when you take this model to the real world data, you will find that the data doesn't look at all like this. So sometimes you see households with pretty similar characteristics x1 to xk. So for instance, they have a very similar income, they have the same number of people in the household and so on. However, their savings rate differs substantially. So this kind of model does not seem to work for every household. So things break down here. Now, an obvious solution is that we say that the economic theory does not necessarily work for each and every household individually, but it holds on the average over the whole population of people. And therefore, each data point that we have is simply a random draw from this large population. So kind of whatever your saving rate is, given your income, this is simply one outcome of a random variable that is like savings rate and income, right? Okay. Now, we already said that the function g that connects the axis with y is a linear function, so we can always write it like this. And the new thing is now the presence of this model error, which accounts for all the differences in the households that have the same x characteristics but different y's. So all these differences come from the model error term. Yeah. And in order to have causality in a microeconometric sense, we need to assume that the x's are strictly exogenous, that we have strict exogeneity. The condition is written here, meaning that the conditional expectation of u given all the x's is 0. So that means that if you have all the information on the axis intuitively, there is no more structural information in the use that is relevant for the mean of the response variable. And we also say that U is mean independent of the axis. Okay, so if you impose strict exogeneity, that also implies that the true model, the true conditional expectation of y, is really a linear function of the axis. You can see that very easily. If you take the conditional expectation of y conditional on the axis, then you can simply replace y by the whole right-hand side. Yeah? All the x's are conditioned on, so they act as if they are constant. They come out of the expectation. And the only thing that is left inside the conditional expectation is really this ui. And by this expression here, it will be 0. Yeah, so truly, the model for y is a linear function of the axis. If that is true, then it turns out that the conditional expectation of y is the same thing as the best linear predictor of y. Yeah? So this thing is the conditional expectation, and it's the best linear predictor. The best linear predictor is something that we can always do, right? We can always find the best linear predictor by simply regressing y on the axis. However, the best linear predictor is not always the same as the conditional expectation. So that's why it says it's the best linear predictor. For it, in order to be the best predictor overall, so that's the conditional expectation is the best predictor, and a normal regression is only the best linear predictor, right? It's a linear approximation to the best overall predictor. And if the true conditional expectation is itself linear, then of course the best linear predictor will also be the best overall predictor. Yeah? And in that case, we can also talk about causality. Yeah? So when I talk about the causal effect of a marginal increase in income, that means I simply have to take the partial derivative of the conditional expectation of y, conditional on all the x's, with respect to the x1 variable. And because the model is linear, we simply get the coefficient for x1 as the solution here. Yeah? So the interpretation for our beta 1 is simply the marginal increase in the expected y conditional on the axis due to a marginal increase in x1. And here, because we condition on all the x's, we keep statistically the rest of the variables fixed. Yeah? So statistically, again, x2 to xk are fixed. The only thing that changes is x1. And if we then find a change in the average y, we say this is a causal relationship. Last thing before the end of this video, is a remark that we can always make the model error to have mean 0 as long as we include an intercept into the model. Right, so the beta 0 here is the intercept. We should always include an intercept in the model, because otherwise we force the regression line to go for 0, and that may induce bias. So always include an intercept. And if we do that, then we can simply redefine the model. Now we have the intercept beta tilde, which contains the original intercept plus the expectation of the model error. And we define a new model error, u tilde, by simply subtracting the expected model error from the model error. And this u tilde, of course, has expectation 0 just by construction. Okay, finally, some remarks. When we say that u is mean independent of the axis, that does not only mean that u is uncorrelated with x1 and to xk, it also means that u is uncorrelated with every measurable function of the axis. Yeah, so for instance, u has to be uncorrelated with the square of x1 or the cube of xk. Independence of u and the axis is stronger than strict exogeneity, than mean independence. Mean independence is again stronger than orthogonality, so that y is uncorrelated. Sorry, I think this should be a U actually. I will change this. U is uncorrelated with the axis, yeah. And the other direction is in general not true. That's something to keep in mind. Okay, so that's the first short video. In the next video, we continue with the pooled OLS estimator for panel data. See you there.